Hi, Justin here, G0KSC, and thanks very much for coming back to the channel. And what a week it's been. I really appreciate your feedback for the previous videos, and they've really taken off, which is great for me. Seeing not just the hit rate going up on these more recent videos, but the followers as well, which has been climbing incredibly fast, much faster than it's been doing over the last few years. But then again, for the last couple of years I haven't been posting too much, so it has given me a great deal of inspiration to keep doing these technical simplifications, if you like, with regards to antennas, and move things along the way. So hopefully this is going to be of benefit and seen as useful in the same way as the previous ones have been for you. So what we're doing and moving on to now is my variant, or if you like, modifications to the J-pole, or the evolution of the J-pole as far as I've see it. And I'm sure somebody else has done something similar in the past, as they always seem to have. But this is sort of my journey, if you like, in the antenna design space for this particular antenna. So with the J-pole as was, this is where we were, and this is on the standard J-pole, and this is the easy neck one. Now I do recommend, I know I said it before, I'm going to see if I can work out how to add a previous video onto this YouTube video, so it's an easy link for you, but I'll put it in the bio bit down below as well, in order that you've got easy reference to the last one where we was discussing J-poles, in case this is the first time you're seeing it. And also the much earlier videos which explain some of the theory in EasyNet, which is this antenna modeling software that we're using. So this is the J-pole that we started off with, and we ended up extending a small section here in order to increase the gain, compress the elevation lobe, and lower the angle of radiation slightly as well. So it was a very small modification which made a difference. The problem with this is that if we look above the antenna and down onto the antenna, so we're going to be sort of putting it upside, not upside down, but looking down from it, from the top. Firstly, this is the side-on elevation from the horizon, so we're looking at it side-on with the antenna standing like this. And if we go to the azimuth plot, so we're looking straight down on the antenna, then you can see that it's fairly omnidirectional, but there is a slight mismatch on this side. It's slightly directional in the direction of the J. It's acting as kind of a very loose director in a sense. So not 100% omnidirectional as we would hope to see. So where my developments took me is to think, well, what happens if we put an element on the other side? So we would have, if you like, a J rather than a W rather than a J. So something along these lines. Now there's a couple of benefits here that come from this arrangement. One is that now, rather than the feed being unbalanced and then having a much more difficult time of balancing the feed point, i.e. any balun that goes onto that J-pole, or the standard J-pole, would need to be have a very high choking impedance to avoid coax radiation. So if it's much more balanced in its approach and the way that the antenna is fed, then much less choking impedance is going to be needed to get the antenna in balance. So with this arrangement, as it is now, we have only had to add the second one, like a mirror image of the first, and then the feed point, of course, is now in a balanced position in the antenna. So it's right at the bottom here. So if we have a look now at the azimuth plot of this antenna, I'm going to have to put this above in free space again and run the plot. You can see it's far more symmetrical than what the J-pole would be. Now for the Hawkeyes amongst us, you'll see that the gain figure is slightly down on what the normal J-pole would be, and you'd be correct in establishing that or seeing that. However, that's because of the directional properties of the J-pole. So it's biased in the same way as a beam. If you put dipole elements that are slightly shorter in front of the dipole in a Yagi, then of course you get gain in that direction and front to back in the other. So where that gain on the standard J-pole is, or that additional gain, is in the direction of the vertical dipole, or the vertical radial if you like. So you have less gain by the same degree in the opposite direction. So although the gain on this W pole, or Falker as I've called it, is slightly less, it's slightly less in pretty much all directions. If you look here, we're 2.46 as it says against 2.64 in these directions. So it's a tiny amount. Now this is free space gain and this is real gain. This is something else that I've spoken about before. You'll see all sorts of published figures for J-poles, but essentially we're looking at a half-wave end-fed dipole as being the radiating element, this bit above here, and the rest of it is matching section at the bottom. We can go into detail in that, but we have done that in previous videos. So let's have a look at a variant of this where we add that smaller section to the bottom to extend it in order to give us the down tilt and hopefully a slight increase in gain that we saw in the variant of that we had on the J-pole. So that comes on to this one here. If it'll open up. Did that work? Oh yes it did. Right. So now we have a situation where we have this extended section here. Looks a little bit different again, but this will do hopefully what it did in the J-pole and give us a slight down tilt. So if we look now, we look firstly above the antenna, and there's a slight increase, 2.67 dB. Was that a slight increase? Let me just check that. Wrong one. And now we should be sorted. So azimuth plot now. Okay, 2.64. So virtually hardly anything whatsoever, but there is a difference. But if we now look at the elevation and angles of radiation, there's your slight down tilt, and when we go to this one and change it, you see it's pretty much along the horizon, so it's a bit more visible. You can see this down tilt, which ultimately once you get it above ground is going to be reflected up. The angular radiation is going to be affected by ground influence, and it's in very high instances where you're on an extremely high tower on the top of a mountain top or something where the difference would be really seen. So that's where we are with this section at the bottom, and just to get some sort of indication as to how that looked when it was built, I've got some photographs here to show. I'm going to have to resize this and bring this down in order it's into display. So this is a basic indication of what a real-world built version of these would be like, and this is obviously just prototyping and testing, so the structure is perhaps a little more clunky than it would be in the real world, and this one was actually produced for a commercial broadcast station around 105 megahertz in Spain, just to get something a little bit different up which could handle the power. And obviously removing coils and matching devices means that you can put a lot more power in without any potential issues there, and obviously having the proper almost pure omnidirectional performance of this antenna over something like the J. So if we zoom in a little bit here, you can see that, as we discussed in the last video, the antenna is adjustable at the top, so we can adjust where the antenna actually sits from a center frequency point of view, and then we have the adjustments of the two tops of the J's in order that you can fine-tune for impedance. We can't move this point because these are fixed, but it was enough to get a reasonable result. Now, if I change over now to this example, which is a 4-meter one, you can see this is a little bit longer and a little bit more of a evolution, if you like. There's a few more tapers on the vertical antenna section, and by tapering the elements in this way, you'll get much less movement in wind, as the much less of the force is transferred at the, down to the base, and there's much more or much less resistance at the top, so it stays vertical for longer in a sense. So that's the first part. We still haven't got the adjustable piece at the bottom, but what we have got, which is not really clear to see here, is this section that's holding the antenna in place is a thick fiberglass round tube, and this thick fiberglass round tube means that it's completely insulated, and the whole antenna sits above the aluminium or the metallic structure that the antenna is supported onto. Also, there's a small piece of perspex here that has been bolted on the opposite side of the feed point. So you've got the two terminals here at the feed point. We can see that actually. The two terminals here at the feed point, and on the opposite side, those two bolts are bolted onto this perspex. What I was able to do here is just heat this section with a heat gun, put the whole perspex sheet into a vise, heat gently either side, and then fold it over on the vise, so you've got that 90-degree bend, and obviously the hole then drilled in order to support the balun. And the reason that we're doing that, as we discussed before, we don't want baluns on or close to the antenna or interfering surfaces, and as this is an active part of the antenna, if that was attached to that or running down from that, then it would add distortion and potentially induce common mode currents, which the balun is trying to get rid of, onto the coax cable. So as with any antenna, the ideal exit point is 90 degrees from the feed point. So it doesn't look best, but it's the most practical in terms of having your focus directly on performance and performance alone. So this is coming out at 90 degrees, and then the coax comes down, and then as a result of that, we can replicate model as best as possible. So to give an example of that and the result, this is the model prediction of what the SWR should be on this one for 4 meters. And some of our American friends actually, while I'm speaking about this, may think, well, you was doing it on 4 meters last time, that 70 megahertz band, which we don't have, and you're doing it on 4 meters this time as well. Why is the reason for that? Well, as much as anything, 4 meters is a band that's used in the UK. It's not a hugely popular band outside of the summer months when it's extremely active and there is some E conditions. But as far as physical size, for testing and prototyping, the 4 meter side is fairly compact in size when you're producing the antennas, and they're not as critically important as what you would have in VHF and UHF, so you can get relatively good and close results to model without being too meticulous in the components or the structure of the antenna. So the long and short is it's the easy way out of or the lazy man's way of design and development in that sense. So I'm going to leave that one there for the moment, because what I'm now going to do is overlay the SWR measured results. So if you look at this here, you can see the center frequency 70.400, and we're at the bottom of the flat part where it's pretty much 1.0 SWR, excellent return loss, and it comes up to sort of 1.2 to 1, a megahertz down from that, because it's 1000 kilohertz either plus or minus 1000, and then 1.2 up from that. And when we look at that here, center frequency is around this piece here where it's 70.4, and you can see that unity part is just below that, so it's only fractionally off of what the measured antenna shows in the real world. And similarly, that what does it say, 1.18 to 1 a megahertz down and a very similar position up. So as close as damn it, this is a pretty good representation of the model. It's very close on either side. So we know we've got something that's going on pretty good. So what's the next step on from that? Well, for me, the next step was to add some collinear elements. We spoke in the last video that we've got 3 active sizes that we can use for single elements that will achieve our low angle radiation: quarter wave, half wave and 5/8. Anything that's longer than that needs to be collineared elements, i.e. a phasing coil to bring it back to the point of 0 and then start the next section again, in order that you can maintain that low angle of radiation. So it would either be a phasing coil, as some of you would know who watch my videos. I'm not a fan of coils, heaters and limiting in so many different ways. So I look to achieve that by other methods. And in this case, you can use a long hairpin in order to bring yourself back to the right point of phase to start for the next element. And that turns into a collinear that, when built, looks like this. So now we've got the antenna with its extended section. We've got a slightly bigger supporting structure on this one from the mast, in order to, because it's longer, it's twice the length in this case. And then this up here is 1/4 inch solid rod that's produced into this hairpin arrangement. And what we did is to cut a thread onto the ends of this with, I don't know if we can see that very well, it's not a very good shot when we zoom in. And then one nut was pulled in all the way right up to the edge of the thread on the inner side, and then one that passes through the boom, and there's that a piece of that very thick fiberglass as a spacer here, so there's an insulator in there. And then the second bolt or nut goes onto the other side to secure and finalize this phasing section to bring it to the start of phase, as it is at the bottom of the antenna, for the next section of element. So this is like a half wave over a 5/8. So there's a 5/8 on top and half wave on the bottom. When we look at this, if we have a look at the extended antenna in model, let's just have a look at this now. That's how it looks. You can see it's a longer section on the top, the 5/8 section, and half wave at the bottom. And I'm going to just take off the dots, so the segmentation dots, and also the wire numbers, so it's easier to see the wires in the model. So you can see there's the Fulker section at the bottom with the little extension at the bottom, and then we've got our hairpin at the center point as well. So when we go back to this, you can see it's pretty much the same replication as what we saw there. So how does that look? So in free space, if we look at the elevation, you can see it looks very different, and we've increased the gain now up to 4.62. Now again, some of you that are not familiar with modeling and real world figures, unlike those that you'll see publicized, this is actually real levels of gain, not the ones that are sort of think of a number and add 50 before the gain figure goes into marketing material. This is what you can expect to see in the real world, albeit this is in free space, so it's not placed above ground. When we place it above ground, then we do get some additional gain depending on the height above ground and the ground conductivity, or what we call ground gain. Although ground gain is quite limited in vertically polarized antennas, but that's the subject for another video. So that's how it looks. From above, it's fairly rounded again, and fairly balanced, because it has the W on each side. So if you look at the here, whereas it's 4.86 at the sides here, it's 4.59. So 4.6, you know, it's about the same, 0.16 dB down on these sides to what it is on the sides where the forks or the vertical radials are. So how does that look when we place it above ground? What have we got here in terms of ground level? I'm going to have to put this up. Excuse me if you're off screen. I'm going to lift this up above ground. So we'll put it 10 meters above ground, and then we'll put it into above real ground. And when we have a look at the model, take it off the center, you can see now where it's placed in terms of size and above ground, 10 meters up. So how does that perform? Well, let's have a look at the, in actual fact, we're not going to do the elevation, are we, without doing 3D? It's going to foul. I'm going to, oh, it is down to 0.1 already. So you can see it looks much more acceptable with fairly low radiation into the upper regions and into open space, with a great deal of emphasis that's now at 4 degrees or 4.3 degrees, and then some sublobes which are quite a way down but still giving some good directional gain. So 8.1 dB, all but damn it, as being where it's at. Now I'll run the SWR for you as well, so you can have a look at that. I'll do that in free space because it's quicker, and I'm going to run it between 70 and 70.8. So you can see it actually does need a small amount of adjustment. It's peaking at the bottom end of 70 megahertz. One of the reasons for that is that when I did this model, it was done using NEC4, and I'm now using NEC5, which is a bit more accurate. So this would have dipped a little bit lower than that, and now it will be it would need some adjusting to get it closer. Now what I'll do, just to give you an example of what it would have said in the NEC4 software, I'll probably be completely wrong now. There you go, it's centering up around the 70.45. So finalization would have been that we'd just add some small adjustments to the vertical sections to bring them up, make them slightly longer, and then it would peak in the middle of the band, as NEC5 is a little bit more accurate than what NEC4 is. So that's pretty much it. I'll bring that back up to the Collinear so you can have a look once again at the 5/8 over 5/8. Now what I am going to do is I'm going to open up a community here. Some of these drawings and some of the EasyNet files, if you want to start seeing these, I'll attach to some of the videos that we're producing and put them down in the comment sections with a link to the g0ksc.co.uk site, so that you can download those files, play around with them and modify them. In the community I will be adjusting some of these for specific frequencies that people want to play with, and maybe also making some drawings for people to build for personal use for individual requirements, in terms of the sizes of materials that they want to use and the frequencies that they want to use. For me, a point of interest is some of the rarity areas, you know, like whereas it's something that's a little bit different. I did some development work on some antennas for an organisation that work out of Norway, where they're tracking dolphins and whales, and it was on a particular VHF frequency, and they're installed onto lightweight ribs which are going off and following these animals or mammals. So that was a pretty cool one to do. It was a little bit different. And then a friend of mine, G8FJG, is into weather balloon chasing. These things put out very low power around the 868 megahertz. And of course the commercial antennas that you can buy for those are very broadbanded, in order that they can cover a lot of frequencies, and that the cut tolerances that these manufacturing companies use won't interfere too much with the SWR. It will still show a very good or a relatively good SWR, but the performance is absolute mediocre at best. So that was a great project, and what I will do, one of the videos that I'm going to do, I'm going to show you the difference in performance between the antennas that I designed for Ron and the general run-of-the-mill, where people are using all sorts of different LoRa antennas and such likes, because his ability to receive far exceeds anybody else by a huge margin. And we know that because the organisation, one of the universities in the UK that collect that data from amateurs and enthusiasts that are collecting the received reports and sending them to them, they collate those and put those into a graph so that you can see what the results of those are. And Ron's is massive by comparison to anyone else that's recording those things. So it's always good to concentrate and work on dedicated, very low noise, highly optimized and very accurate models in new areas or new areas and new frequencies for me. So let me know your thoughts and suggestions on where to go. I do have quite a plan of subjects that we're going to be covering over the next month or so, but always looking for new areas to cover which would be of interest to you, because if they're of interest to you, then they're going to be of interest to someone else as well. Thanks for bearing with us today. If you made it this far, thank you very much indeed. And the next thing that I'm going to be doing is adding some freebies and some giveaways, which are going to be noted at different points in the video. So hopefully you'll pick up on those as we go forward, and look forward to, hopefully, fingers crossed, seeing you in the community in due course as well. So that's it for now. Happy Saturday. Bye.